You're listening to Würth Elektronik's What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We're going to be checking in with leading industry experts and our very own Würth Elektronik technical specialists. We're going to shine a light on interesting topics like energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Würth Elektronik's What's Up podcast. Now, it's very common knowledge that Würth Elektronik is a leader in the industry of magnetics and transformer design. Now, even though a transformer is a passive component, it has a great influence on the overall electromagnetic compatibility, or EMC, of the power supply. In today's podcast, we're going to highlight what we can do to keep the emissions low. We'll start off with a discussion of the properties of the transformer that impacts EMC, and also show what techniques we can use and implement in the construction of the transformer to minimize this impact. Finally, we're going to show examples of bad and good design practices, ranging from flying leads to shielding windings.
I will talk about transformer design for EMC. I am a design engineer for power transformers and custom magnetics here at Würth Electronics Midcom. So it is really our daily business to develop new product, new power transformers. And of course, when we develop a new product, we try to implement all these nice features that make it a good transformer. So I will talk today about parasitic properties of transformers and the transformer impact on EMC, electromagnetic compatibility. This is a particularly interesting topic because a transformer is a passive component. So at the first glance, you would say, well, how can it impact the EMI? It's passive. It will only transmit or radiate whatever we put into the transformer with our power supply, right? But if we take a closer look, we will see that the internal construction of the transformer can influence the EMI behavior. So at the beginning, I will give a very quick theoretic introduction about conducted and radiated emissions, but I will keep it short because the main purpose of this webinar is to show you what we, Würth Electronics, can do as a manufacturer to make the transformer as good as possible. So I will really focus on the internal construction, how the windings are positioned inside the winding window, and so on. So I will show a few good EMC design practices that we always try to follow. In the end, I will also show the influence of shield windings on the EMI behavior and additional measures what we can do. So to get started, here's a schematic of a transformer. In the center of the schematic, you see the ideal transformer with just a primary inductance, a secondary inductance, coupled with a magnetic core. But of course, in reality, such a transformer has also many parasitics. So we have, of course, a resistance on the primary and on the secondary winding. We have a leakage inductance, which is a measure for the amount of magnetic coupling between the windings. Then we have a intra-winding capacitance. This capacitance exists on both sides, on the primary and on the secondary. And it is really, it defines how strongly the individual turns inside one winding couple to each other. So depending on how it is wound in one layer or in two layers, or maybe in even more layers, the capacitance of each winding can change dramatically. And then we have the interwinding capacitance, which is here shown as the capacitance between primary and secondary. And to get this webinar started correctly and no one falls asleep, I would like to ask you a question before we get into it. So just imagine a case where you have a conducted noise, a conducted emission in your power supply and you want to get rid of it. And you think that maybe it might be the transformer who causes the problem. So here comes the question. Which parasitics do you think we should optimize to get rid of this conducted emission? And I will give you now about 20 seconds to think about it. If you want, you can also write your answer in the chat. And on the next slide, I will present the solution. Okay, here we go. So we distinguish between conducted emission and radiated emission. A conducted emission is always transmitted by the electric path. So we talk here about an isolated transformer where primary and secondary are electrically not connected. They are only connected by the magnetic core. And as you see here, also by the interwinding capacitance. So if we apply a higher frequency signal, of course, the impedance of the capacitor goes down and it becomes conducting. So the noise that we inject into the transformer can pass through the interwinding capacitance. It is therefore a main target to reduce the interwinding capacitance if we want to improve the EMI behavior of the transformer. On the right hand, you see the radiated emissions. This is the high frequency regime in the, let's say, more than 10 or 30 megahertz. In this regime, the source of the noise is really radiated into the air. So we consider the transformer in this case like an antenna. Whatever signal we put into the transformer, it will be emitted as radiation. And now if you think about the wire that is inside the transformer, a very typical length of wire can be in the range between 50 centimeter and maybe 2 meter. And anyone who has a radio station at home to receive radio signals, to listen to music, you know that maybe a 70 centimeter antenna is perfect to receive such signals. So we are here really in a range of wire length that can work as an antenna. And this radiated emission, it can couple into everything, into PCB traces, into other components, into cables, even into external circuits surrounding maybe your power supply. So in order to keep the radiated emission low, we want to improve the behavior of the transformer. Now we go a little bit into theory. We look at the switching profile of a flyback transformer. And on the right-hand side, we see the resulting noise spectrum of this transformer. And we see very clearly that a conducted noise, a conducted emission, shows up in this spectrum at higher harmonics of the switching frequency. So in this case, the switching frequency is around 115 kilohertz. And here we see a very, very big peak at 230 kilohertz. So we know the source of the noise is the switch. When the switch opens and closes, we see very steep slopes in the voltage diagram, in the voltage path. And therefore, it creates EMI issues at those higher harmonics. So we see another peak at 3 times the switching frequency, and it goes on into a very high frequency regime. Then here beyond 10 megahertz, we see another peak, a very big one. This is what we consider already as radiated emission. We see it here on the next slide. Now this is a close-up into the high frequency regime. This is what we call a resonance phenomena. So parasitic properties on your power supply can form LC resonators. And whenever the switch turns on or off, we have a steep slope, a fast change of voltage. And this change of voltage can excite an oscillator. So those unwanted LC resonators on your circuit, on your PCB, they start to ring. And with this ringing, we have very high frequency signals in the circuit. And again, the transformer will just be the antenna who emits the signal. So most of the time when your power supply fails the EMI test, the transformer is not really the root cause. It is just the result, the medium which transmit the noise to the surrounding. With this, we go into practical approaches, how to improve the transformer. And the very first thing, and probably the most important thing I want to show you here, is how to connect a transformer on the power supply. It is very, very important to connect the start of the winding to the switch. So you see here in this diagram, the transformer is shown as L1 and L2. This is primary and secondary winding. And the start of the winding is here indicated with a black dot. And if we now look into the construction, this is a cross section of the transformer. You see here also the start of the winding indicated as a black dot. And as you can see, the start of the winding is of course buried very deep inside the transformer. So the remaining turns, the remaining winding is wound over the start. It buries the start below. Then we have here an interface to the secondary, and on top the secondary winding. So if we now connect the switch to the start of the winding, we have the source of the EMI, the steep slopes in the voltage. We have this buried very deep inside the transformer. And if we look at the equation, we see the common mode current is proportional to the capacitance and to the change of voltage, du by dt. So what we have connected here to the switch, we call this the switching node, or the high du by dt. And the end of the primary winding is called the quiet node, or the low du by dt. So we really see, as we go along the winding, the voltage increases if we come from the end, or decreases if we look from the start. And not only the voltage decreases, but also the change of voltage. So the du by dt decreases as we go along the winding. And you can see here very clearly the interface between primary and secondary is here, those yellow lines. This is where the insulation tape is. So looking at the interface, it seems like here's now already a low du by dt, which will result in a low common mode noise. Then if we have connected the transformer correctly to the switch in the correct orientation, and we still have a problem with EMI, then what else can we do? There's a very clear guideline from our side that smaller transformer can help to reduce EMI noise. Why is this? It's a very simple answer. A smaller transformer will have less capacitance because just the size is smaller, right? The interface between the windings is smaller. It will have smaller lead wires and even a smaller length of total wire inside the transformer. So we just have a smaller antenna. It has also a smaller gap in the ferrite if we talk about a flyback transformer with a gapped core. And in the end, this will also result in a lower leakage inductance. So overall, we expect less conducted and less radiated noise in a smaller transformer. There is one challenge though. If we make the transformer smaller, what happens? And of course, it can handle less power. So what do we need to do to get the same amount of power with a smaller transformer? We need to increase the switching frequency. And if we do so, we probably end up with another problem just somewhere else on the PCB. Maybe now we fail the EMI test at a different frequency, at a different position. We don't know. Anything can happen. But from a transformer point of view, a smaller transformer is better. Now we can look into the internal construction of the transformer. And I mentioned in the very beginning that the interwinding capacitance is the most important property which we want to optimize. Looking at the cross section, this transformer looks very much like a plate capacitor. So the primary and the secondary form solid metal plates which are coupled. And from our days at school, we maybe still know the equation to calculate the capacitance of such a plate capacitor. It depends on the surface A and the distance D. So basically all we can do is either reduce the surface A or we increase the distance D. And here's how we do it. We can either use a margin tape on both sides. So you see here in this picture, the primary winding uses the complete space available in the bobbin. Now, if we insert here a spacer on the side, we would effectively reduce the width of the winding, and with this we would also reduce the surface area A, the overlap to the secondary. The other thing we can do is to use a special bobbin with two winding windows. You see this here in this small picture. Here the primary and the secondary, they are not wound on top of each other, but they are wound next to each other. And in the middle there's a solid plastic spacer which keeps them apart. We can define the thickness, maybe 1 millimeter, maybe 0.5 millimeter. And this is very effective because now we have reduced the surface area basically to 0, right? They are not wound on top of each other. They have only, looking at the thickness of the winding, this is maybe less than 1 millimeter. So they only are side by side with a very small overlap. The other thing we can do is increase the distance. So you see here the interface between the primary and the secondary is defined by these two yellow lines of tape. Now, if we put four layers of tape instead of 2, obviously we have doubled the distance between the windings. There is one problem. Both of these measures, both of these changes will directly affect the leakage inductance. If you think about it, it is very clear. Both the capacitance and the leakage inductance, they define how well primary and secondary couple to each other. So for the leakage inductance, we try to achieve good coupling. We try to get these windings as close to each other as possible. Sometimes we would even wind them together at the same time in a bifilar winding step to have the best overlap possible. But then for the capacitance, we want them as far apart as possible to get low coupling. So it's always a trade-off. We need to find what the power supply really needs. In most cases, the leakage inductance wins. So we have to optimize the leakage inductance to make the transformer work in the application. Because otherwise, if the leakage inductance is too big, you will just need a huge snubber circuit, or you will put a lot of energy into your switch. It might break the switch. But then we might end up with a big capacitance. So it's a trade-off, a case-by-case scenario. That's one of the main reasons why we offer custom magnetics, because every power supply is different and we always need to optimize it for the application. And we have one little choker, which is the dielectric constant down here, the epsilon 0 and epsilon r. the dielectric constant will not affect the leakage inductance. It's not a magnetic property, it's just a dielectric property. So the material between primary and secondary has certain dielectric. If we reduce it, we can also reduce the capacitance without affecting the leakage inductance. So we can use varnishes or potting compounds with low dielectric properties, or probably sometimes it's best to use nothing at all because air is already pretty good, right? It has a dielectric constant of 1. Okay, then in the next step, if the EMI behavior of the transformer is still not good enough and we need to further improve it, we can try to insert a shield winding. Here on this slide, we talk about a internal shielding, which means the shield winding is positioned between the primary and the secondary. In this case, it is a copper foil. You see in these pictures how it is manufactured. First, the operator would solder a lead wire to one end of the foil, so we can later connect the start of the foil to a stable potential, for example, to ground. Then the foil is wrapped into insulation tape, and then it is inserted into the transformer. I think everyone knows why we need insulation tape on the copper foil. The foil is inside the winding window, so if the start and the finish of the foil would touch each other, this shield winding would form one turn inside the transformer, and the turn is shorted to itself. So if we would do this, we could only measure leakage inductance then on the primary side, and all the magnetizing inductance would be gone because it just induces circulating currents inside the shield. So we must be very careful not to short the shield winding to itself. Here on the right-hand side, you see a test which we did. It's a 20-watt flyback transformer in a switch mode power supply. We tested it 2 times with and without shield. And you see very clearly how strongly the noise is reduced with the shield winding. Then if the copper foil is a little bit too expensive for the application, just if the transformer is very much cost driven and you want a cheap solution, then we can also offer a wire wound shielding. It is physically the same. We still put a shield winding between the primary and the secondary. The shield winding is not allowed to short to itself. But this time we wind the shield with wire instead of foil. So here shown in the schematic, you see a primary on the bottom, then one layer of shield winding, and then a secondary on top. And we have 2 ways of manufacturing it. Here, this one, we start the shield winding on a regular pin of the transformer. Then we wind it with our automatic machine. And then we cut the wire tail, and we can bury the wire tail between 2 layers of tape inside the winding window. This is basically this gives the best performance for a wire wound shield. But it is still a manual process because a person has to take this wire tail and put it in the correct position and fix it with tape. The much more elegant version, if we have 2 open pins on the transformer, so 2 pins that are not in use, which we can now use for the shield winding. We can start the shield winding on 1 pin, wind the shield, and then terminate the finish just on another pin, one that is not used. It is then important for the customer to connect only one side of the shield winding to the stable potential, and maybe we can cut the other pin away so it doesn't disturb. And the benefit of this method is it is fully automatable. So we can just put the transformer on our automatic machines. We can program everything, and it will automatically put the shield winding in place. So now you might ask me, well, if it's so easy and we can do it automatically, why do we not put it on every transformer? The answer is simple. Even though it can be done automatically, the shield will still occupy space inside the winding window. So here in the schematic, we exaggerated it a little bit, but you see here the shield takes about 1/3 of the available winding space. So of course, everyone tries to optimize his power supply for the best efficiency, and every point of percentage counts. So definitely we want to use all the available winding space for the actual winding that carries the current, right? The primary and the secondary. So if not absolutely needed, we would try to skip the shield winding, and we only put it if the customer really requires it. Maybe the customer has seen EMI issues already, and of course, if we know it's needed, then we can put it. In a case where the transformer is completely full and we are not able to put the internal shield winding, as I just showed, then we have also the chance to put an external shielding around the transformer. This is what you call a flux band. It can be added after the transformers have been built already, so it is completely external. We don't need to open the transformer. The physical principle is different. While the internal shield winding really fights against the root cause, so it removes the noise between primary and secondary before it couples. So it basically redirects the noise to the stable potential. Here, this flux band, it only removes radiated noise. So it can hardly fight against conducted emission because it is around the transformer, right? It can only shield what comes out of the transformer as a radiation. It is expensive to add this shield winding because it is a manual process. In contrast to the internal shield winding, now on the external, we can connect start and finish of the foil together. So this one is allowed to short to itself. We usually even add a little spot of solder to guarantee a good connection. Here's a little trick that we tried in the past. Instead of wrapping the whole transformer into a flux band, we can also just put a little sticker of a copper foil onto the side of the core. The benefit is, of course, it is less labor, so it's much quicker just to put the sticker. We can still solder a lead wire to the foil, so we can connect the foil and the complete core to ground, to the system ground. And because the core is conductive, a ferrite material, it doesn't conduct very well, but it is a conductive material. The complete core is grounded anyways, even if we only connect one little spot to the ground potential. And it showed pretty good results. So we have some active parts that use this method. An even better solution would be to use an external cap for shielding. So here you see, for example, an EFD20 transformer. It is 20 millimeter wide. The EFD shape means that it is very flat. And on this package, we have by default a metal cap on top. The main reason is not for EMI purpose. The main reason is to get a flat surface for the pick and place machine, because you can see here in this picture the top surface of the transformer is not very even, it is not flat. So it would be difficult to pick and place this component with an automatic machine. But nevertheless, the metal cap has exactly the same effect as a copper foil. It will shield all radiated noise coming out of the transformer. And this cap is highly available. We put it basically on every transformer of this package size, so there's no lead time issues or whatever. It gets even better if the cap has an additional pin to connect into the PCB. So here on this example, here you can see it clearly from the metal cap. There's a little pin, and then you can really connect the core and the metal cap to your ground potential. The most elegant way, without any effort, is to use our EP package. This transformer has a completely closed ferrite core. We have it in different sizes, ranging from EP5 to EP13. I think we even have an EP15. It doesn't add any cost because ferrite is cheap, and we have this in big quantities. It shows excellent EMI performance due to the fact that the core is closed already. Very little radiation can come out of the transformer. And with this, I would like to come to a few topics and things which we try to avoid in a good transformer design. And one of them is definitely flying leads. Sometimes it is needed to have flying leads. In most cases, this is due to the isolation requirements. For example, if someone needs a reinforced insulation for a pretty high working voltage, it can happen that we need to meet 10 or maybe even 20 millimeter of creepage distance between primary and secondary. And in such a case, we would use a triple insulated wire on the secondary side, and we would just extend the wire outside of the transformer, as you can see it here. So the wire exits the transformer, and as long as the insulation is not damaged anywhere, we can meet easily 20 millimeter of creepage. So the purpose is to move the point where it's terminated away from the transformer. The problem with this approach is flying leads make great antennas. These flying leads, they run very often parallel to PCB traces. So they couple strongly into your PCB. So from our side, there's only one thing to say: please try to avoid it. It is also not very good for manufacturability, and even worse for the end customer for assembly. So if you have flying leads, every transformer must be assembled manually, because basically no machine can insert these flying leads into the PCB and solder them automatically. Another thing that we try to avoid is the EI core style, where one half of the core looks like an E and the other half looks like an I. This was very common for 50 Hertz power transformers in the past, and people used tape to create a uniform gap on all the core legs. So we had 3 unshielded gaps, and those gaps on the outside, they of course radiate a lot of emission into the air surrounding the transformer. It is much better to use the modern approach with a regular power ferrite, where only the center leg is gapped. So in this case, we have no gap on the outside. So basically there's nothing to shield because no radiation comes out here. And a little bit a bigger gap in the center leg. But this gap is covered by the winding on the left and on the right. So the radiation that comes out of the center gap, it will be dissipated, at least partially, inside the winding. Of course, this will affect a little bit the efficiency. The effect is called fringing. So the magnetic field that comes out of the center gap will cause AC loss in the winding itself. But any loss you have, you can be sure that at least it will not show up in your EMI spectrum.
We understand that not all images and videos show up on each podcast streaming network. So to replay the full webinar with video, visit our video center at www.we-online.com or visit our YouTube page. You can also find the entire selection of EMC components online, as well as transformers, and talk with our custom transformer design team at Würth Elektronik Online, www.we-online.com. You're listening to Würth Elektronik's What's Up Radio podcast, where each week we're seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Würth Elektronik technical specialists. We're going to shine a light on topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Würth Elektronik's What's Up podcast.